Electroplating uses a type 3 electrolytic cell to plate a thin layer of one metal on an object composed of a different metal. We'll illustrate the process with an example. Let's say we have an iron spoon and we want to plate it with a thin layer of nickel metal. We'll put it in a container. We'll represent some of the iron atoms in the spoon. And we'll add a nickel metal electrode on the other side of the container. And we'll represent some of its atoms. We'll attach a power supply and wires. Notice the negative terminal of the power supply is attached to the spoon in this case. The object to be plated must always be connected to the negative terminal. Now we'll add an aqueous solution of nickel 2 sulfate to the container. We'll remove the water molecules for simplicity, but remember they are still there. Remember, in an electrolytic cell, the positive electrode is the anode, and the negative electrode is the cathode. There are three main requirements we always need to remember for electroplating. Number one is the object that is being plated must be the cathode. In other words, it must be connected to the negative terminal. The second is that cations of the metal we want to plate on the object must be present in the solution. In this case, we want to plate the spoon with nickel, so nickel 2+ ions must be present in the solution. That's why we used a solution of nickel 2 sulfate as our electrolyte. The third requirement is the anode should be made of the metal we want to plate the object with. In this case, we want to plate the spoon with nickel, so we're using a nickel electrode. It would be a good idea to pause the video at this point, take a screenshot, and print this, so you have a reminder of these three requirements. As we proceed, you'll see why these are important. Because the nickel electrode is positive and the spoon is negative, cations will tend to move toward the spoon and anions toward the nickel electrode. We know that oxidation occurs at the anode and reduction occurs at the cathode, but what is oxidized and what is reduced? The nickel 2 sulfate solution contains nickel 2+ ions, sulfate ions, and water. And the nickel electrode is made of solid nickel metal. Now the cathode, or the spoon in this case, is made of iron. But remember, the cathode metal never reacts. Metal atoms cannot be reduced, and oxidation cannot occur at the cathode. So we don't consider the iron the cathode is made of at all, as it doesn't react in any way. What we do is underneath these, we write a C- on the left for the cathode, and an A+ on the right for the anode. Reduction occurs at the cathode, and oxidation occurs at the anode. Either Ni2+ cations or water will be reduced at the cathode. At the anode, there are three candidates for oxidation. They are water, the sulfate ion, or solid nickel. Now we'll go back to the cathode. To find out whether Ni2+ or water is reduced at the cathode, we look at the overpotential arrow on the left side of the reduction table, and the half reaction for the reduction of Ni2+. We see that the nickel half reaction is higher than the arrow, which means nickel ions will be reduced at the cathode. And the half reaction for this reduction is Ni2+ plus 2 electrons gives nickel solid. We'll make a note of this up here. To find out whether water, the sulfate ion, or nickel metal is oxidized at the anode, we go to the right side of the table and find the overpotential arrow for water, the half reaction for sulfate, and the half reaction for nickel metal. The oxidation potential of the sulfate ion is negative 2.01 volts. Water behaves like its oxidation potential is about negative 1.38 volts. And nickel metal has an oxidation potential of positive 0.26 volts. Because nickel has the highest oxidation potential of all three species, it will be the one that is oxidized. We can also look at this another way. As we move down the right side, reducing agents get stronger, which means their tendency to be oxidized increases. So the lowest one, nickel in this case, is the one that is oxidized at the anode. The half reaction for the oxidation of nickel is this half reaction reversed, which is Ni solid gives Ni2 plus 2 electrons. So we can say that the half reaction at the anode is Ni solid gives Ni2 plus 2 electrons. So now we have the half reactions at the cathode and the anode. Notice they are the reverse of each other. So looking at our diagram of the cell again, we can say that the half reaction at the anode is the oxidation of nickel solid to form nickel 2 plus and 2 electrons. And the half reaction at the cathode is the reduction of Ni2 plus to form nickel metal. Now we'll focus on the cathode. 2 electrons will be pushed out of the power supply, go through the cathode, and move on to the Ni2 plus ion. As the nickel 2 plus ion gains 2 electrons, it forms a nickel metal atom. This process will repeat itself with another nickel 2 plus ion. And it forms another nickel atom. The nickel metal atoms that are forming will keep on forming and gradually coat the surface of the spoon, forming a thin plate of nickel on the spoon. This is why the process is called electroplating. It is easy to see that as reduction of Ni2 plus ions continues, that these nickel 2 plus ions are getting used up. So will they become depleted? The answer is no, not as long as we have a nickel anode. Now we'll focus on the anode. What happens at the anode is a solid nickel atom, which we'll show in the equation, will lose 2 electrons to become a nickel 2 plus ion. The nickel ion will then leave the metal and dissolve in the solution. This process will repeat itself with another nickel atom. The new ion that forms will also leave the nickel electrode and go into the solution. Looking at the whole cell, as nickel 2 plus ions are formed at the anode by oxidation, they will keep on replenishing those used up at the cathode by reduction. Going back to the anode, we can say that as the nickel anode is oxidized and ions formed go into the solution, it will lose mass. After a lot of use, the nickel electrode would disintegrate to a point where it is no longer useful. It is replaced with a new one before this happens. Now we'll look at a diagram of the whole cell without representing all the atoms. Knowing the half reactions at the anode and the cathode, we can imagine that as this cell operates, the nickel metal electrode will get oxidized and gradually shrink in size, while the iron spoon will gradually be coated with a thin layer of nickel metal. So in summary, the type of cell used in electroplating is a type 3 electrolytic cell, in which the object to be plated is connected to the negative terminal and becomes the cathode. A nickel metal electrode is connected to the positive and becomes the anode. And the electrolyte contains cations of nickel, the metal we want to plate on the object. Oxidation of nickel to form Ni2 plus cations occurs at the anode. This will cause the anode to gradually dissolve, but keeps replenishing the solution with Ni2 plus cations. And reduction of Ni2 plus cations to nickel metal occurs at the cathode. This newly formed nickel metal will coat the surface of the spoon, forming a thin plate of nickel. The function of the power supply is to provide the energy to keep this whole process going. It pulls electrons away from the anode, causing it to oxidize, and pushes these electrons onto the cathode, causing reduction of Ni2 plus cations.